So our speaker for today is Krishna Kumar, and he will talk about elliptic curves over arithmetic fields. Please.
Thank you so much, Philip. So good morning, everyone. So welcome to the talk. So as I've already said in the group, it's going to be like a very easy peasy talk. You can just, I see you already have coffee, so really good. Just sit back, relax. It's going to be like a movie. Yeah, so no rough stuff, no complicated proofs. Maybe I give some idea somewhere, but I think like all the theorems I'm going to state today are like really revolutionary theorems. So it's like I can't give a lot of proofs in that within that. Okay. So just to before starting, I would like to give a big picture of what's going to happen here. So the topic is like elliptic curves or arithmetic fields. So by arithmetic fields, I broadly like we are going to see the field. There are like two broad types of fields which we are going to see today. Like one is the finite fields, which we have already discussed, which has only finitely many points. And the next one is the number fields, for example, Q and finite extensions of Q. So these are the two protagonists today. They're going to like rule the whole talk today. So and yeah, so maybe finite fields or like finite extensions. Suppose U root D, where D is a non-square integer. And like if I want to sum up the whole talk into a single line, it's like we are going to do some enumerative stuff today. So the idea is like you have elliptic curves defined over some field. Then you can consider the set of rational points, which I'll define what it is. So the set of rational points, we'll see it forms a group, and we are interested in seeing when this group is finitely generated or how many points does this have. So this is one whole thing which we are going to do today. If I want to sum it up really fast. So. And like I would like to divide the talk into two. So one is like we have seen this like over finite field. So here there are some nice things you're going to see on finite field, some theorems and consequences, and on the other point, on the number. So for finite fields, we'll start with say bound theorem, which in particular says how many points does how many rational points are there on elliptic curve defined on a finite field. So and then like as a consequence, we'll see some application to some character sense. For example, like you can use this theorem to have upper bound to some characteristic functions, for example, if you want. And then yeah, the second part, like there's only two parts. The second part is like mostly on the while conjecture. These were like a series of conjectures made by Andre Weil over of the set of rational points on defined over finite fields. So we're going to see the three statements of Weil conjectures. So these three are in particular, these three are like the things which L function we believe would satisfy. For example, here we would see what Weil zeta function is. So for example, while zeta function is defined for any smooth projective variety, so we give a general definition and a general equation of that, and then we try to see how simple it is for elliptic curves. Yeah, and coming to this part, we have the theoretical Mordell-Weil theorem. So Mordell-Weil theorem in particular is a generalization of Mordell's theorem. So Mordell consider a set of rational points or elliptic curves over Q, and Mordell-Weil theorem is a generalization in a sense that not just elliptic curves but also over abelian varieties, defined over not just Q but extensions of Q number fields. So in particular, this says that the Mordell-Weil group is exactly finitely generated, for example, and we know elliptic curves are like smooth projective varieties of genus 1. So Mordell-Weil theorem concerns like for elliptic curves genus 1, and there's also a generalization to higher genus called the Falting's theorem, which is proved by Gerd Faltings, for which he also received a Fields Medal. he received for like proving three conjectures, and one was the Falting's theorem, which was called the Mordell's conjecture. After its proof, it's called Falting's theorem. So this is in particular for hyogens. And then and this, like there's going to be interlude. So then you're going to see a I know if you have seen this movie, you know probably what it means. So we're going to have there's a nice categorization of primes defined over elliptic curves. So depending upon whether the prime divides a discriminant or like the C4 divides a discriminant, then we can categorize that each prime into either it's good, bad, or ugly. It's not the real name. I'm going to say what the real name is, but just as a warm up, keep this in mind. But this is actually good to keep in mind. For example, if you want to, is well enough to do it. So, and I would say why we do this is we are going to define what's called this Hasse Weil function, which is just we already have a Weil function. Hasse Weil function is for number fields, for abelian varieties over number fields. So in particular, like it's maybe like a counterpart of this. So we need this one to define a Hasse Weil function, for example, and at the end maybe space here. So we are going to end the talk with the BFD conjecture, which is the Birch and Swinnerton-Dyer conjecture, which is like one of the 8 millennial problems. I think it's right. Yeah. 8 millennial problems, which is like till date it's not solved to full generality. So we'll just state what the conjecture is, and we'll see how it's related with the Hasse Weil function. And we'll give one. Just there are like a lot of applications, but we'll just give one number theoretic application of that, and we'll end it. So I think it's going to be fairly effective. So before that, I would like to like write some nice already said things because someone used in the talk. Like for example, one of the equivalent definition of elliptic curves is via Weierstrass equation. So I'm going to keep this part as a black box. I'm going to keep this because I'm going to use it in later. One could define elliptic curve to be defined by this Weierstrass equation. Also in arithmetic PK. So and then if further the characteristic of the closure of K is not true, then we can sort of like use a completion of square method to simplify this equation. So one could also continue with this, but then like a lot of things simplifies if we are not in characteristic two. For example, you can replace y by this guy here. So if you do this, what we get is like an equivalent sort of elliptic curve, which is defined by this equation. So in particular, we are going to define the discriminant and the J invariant with respect to this equation. So where like V2 is a square plus 4 into and this. Yeah, so one good way to remember this is like if you have V2, then you just like multiply this and this, it's 2. And 2 times 1 is 2. And if you see 4, like it's 4 times 1 and 1 is 3, for example. This is like shortcut if you want to remember it. And then using this, one defines the discriminant. So and then we have the J invariant, which is 3 power 4 by the discriminant, where C4 power 3. The C4 is just C2 squared. Okay, so we don't have to care about this for a while, and we'll come back to it. Okay, so the Hasse bound theorem gives us a bound of elliptic curve over finite field. So let's just like fix the notations here. So take an elliptic curve E over, let's say, finite field Q with Q elements. So in particular, this field only has Q elements finite. So then what does the theorem say is like if you, and yeah, by E of K, we mean the set of point K rational points on for example, K rational points are exactly those points in those are exactly those points x, y in K2, which satisfies this equation. So if you just plug it in, you're gonna get that's gonna satisfy this equation. And there's always one point at infinity which always satisfies it. So set of all rational points is like those points which satisfy this plus one always. So and over finite fields in particular, we know that this should be finite. This can't be finite. Because field itself has only finite elements. So the theorem says that this bound here, like pretty accurate. So this means that like the number of rational point is very close to Q plus one. So then you take the approximation. So like before proving the theorem, one can like really, because it's a finite case, one can really see it by probability theory in some sense. So what happens is like if you see this equation, so x is a cubic and y is a quadratic. So which means like for each value x, you get at most two values of y. So for example, like there are only Q points in the field. So each Q point of x gives at most 2 points to y. So which means like you can at most have 2 Q points at the max and 2Q plus 1 because you have the point at infinity. And like if you have any quadratic equation and quadratic equation defined over, for example, x squared plus 1 defined over C as a solution. But x squared plus 1 defined over R doesn't have a solution. So there's like a 50-50 chance. If you have an equation, there's like 50-50 chance that it's either solvable or not solvable. So which means like out of 2Q, you only have Q chances. You don't have 2Q chances. So in particular, that's the whole idea. So in particular, you have Q plus 1, which is this one here. So this was like conjectured by Henry, I think, no, Emil Harton, and it was proved by Hasse in like 1930. So he solved this over maybe I can just.
All right.
Yeah.
How does K relate to a Q?
K is a Q here. So.
Okay. It's just the base.
No, but this I just like this is not related to this theorem, but I'm just stating E of K is set of all K rational points of E. If E is defined over K.
So yes, in the bound, you just write the E of F cubed.
Right. Oh, now it's okay. No, thank you. Okay, so we'll just have a really brief look at the proof. So the idea is like so over elliptic curves, you always have this Frobenius map. In particular, since it's over FQ, we have the Q to power Frobenius map, which takes each point, which Q to power. So and then there is the fact that the Galois group of this equation. So in particular, it's a profinite group, and this group is like it has a profinite topology, and this group is generated by this Q power map. So this is like a highly non-trivial fact, which we're gonna put it in the black box. So this so I think what we get is like a point is a rational. Will be FQ rational point if and only if this point is fixed under detached. So we get this one. This is due to the Galois group which I mentioned. So and then in particular, what we see is like this is you could try to reformulate this in terms of kernel, this identity minus p. For example, identity map takes a point to itself, p to p, and phi of p takes p to p. So this is exactly, or all the three is exactly like the kernel of this map. So if one takes I to p is just like p, which is plus b. So the kernel is encoded in this consensus. So and then like there's another non-trivial fact which says that the kernel. Sorry. So then now we are going to count the points, which and this what we get is like we count the irrational points. This is same as the number of points in the kernel. For this. So, and in particular, we're going to use these two nice facts. It says that if we are on a positive characteristic, we already know it's a positive characteristic, and by the big curve for this one, and so this notation to say that there's a acute curve for this map. So this map, and we take like 2 points, two integers. So then this map, we're going to define in a different way. So m plus n phi, this map is separable. So it's separable if and only if this p doesn't divide n. Example. So, and in particular, what we can see is if we take m to be 1 and n to be minus 1, we exactly get this. So here 1 replicates to being identity, for example. So this could be also written as 1 minus p. So where m is 1 and n is minus 1. So we exactly get this 1 minus p now. So what we now know is this 1 minus p is separable. So, and then what we have another practice like if a map p is separable, then in particular p is unramified. And the kernel of this map is exactly number of points of the kernel is exactly the number of the degree of p. For example, the degree here is q by the Frobenius. So if we just plug in these two points here, what we get is the number of points in the kernel is exactly the degree of p is exactly q. So yeah, there's like only one step now, which is just to use some form of Cauchy inequality to prove to some of the theorems. Which I'm not going to prove, I'm just like, briefly say. So it says that if you have any abelian variety A, this also works for the gender abelian group. So here A is just E of FQ, for example, set of reference points. So it's abelian group. It's not just a group, but abelian group. So what does Cauchy inequality say? It's like if you have such an abelian group, and if you have a positive definite quadratic form. So in particular, this degree map is a positive definite quadratic form. So how you define a degree map is like I think like in last talk we saw between isogeny is an endomorphism of elliptic curves, for example. So this is like you take isogeny and then you give a Q. How do you give it? So if you have a map F, you just send it to the rank of F star, where F star is so you can see E here. E is an abelian variety, in particular it's a variety. So variety of always, so you can also see this E. So it comes with a sheaf of rings, for example, or just a variety as a function field, for example. So if you have a map from say C to D, there's a map of function field in the opposite direction. And for sufficiently nice objects, for example, if they are irreducible, this is a extension. It's a field extension of this one. So a field extension is particular an integer or a natural number. So you just send f to the degree of field extension. For example, that's the rank factor. So on that we can check that it's a positive definite quadratic form. So if you have a positive definite quadratic form, then the property inequality forms. So for two elements, okay, what we have is it's just a classical of this path inequality. In particular, we can see that d of q, the degree of q here is just like q here. You just substitute it and then like you find that inequality satisfied. So it's fairly simple. You have any questions on this?
Let's have a couple of remarks.
Yeah.
Give an insight on this. The first one is that the Hasse bound in fact tells you that whenever you take prime of a prime power, which is at least 7, then this means that any elliptic curve for this finite field has a non-trivial solution, because this means that the distance between the number of solutions and +1 is always bigger than 0. And the second one is just that this thing of the function field extensions is exactly like the complex geometry case at the morphism of compact Riemann surfaces, because the theory of algebraic curves is modeled exactly to mimic the complex case.
Yeah, so, thank you so much. So on a quick application of that is computing the characteristic sum. So, for example, case at q, and here we assume q to be odd, which means like it is all the prime except 2. Can use this Hasse theorems to to deduce certain characteristic sum. For example, define a polynomial f of x to be x cubed plus x squared plus cx plus d. So, and you can define a characteristic function on the set of all units of k, which takes either +1 or -1. How we define it is like a value p goes to 1 if and only if p is a square number. So it's in particular it's a degree 2 characteristic. Yeah, so it's a character of order 2. Sorry, and p goes to -1 if yeah, it's not a square of any, as simple as that. So what we do now is like we can extend this also to the 0 by saying that chi of 0 just goes to 0. So we see that chi can take practically 3 values. It can get either go to 0, it can either go to 1 or -3 values. Sorry, p is any element in case.
Yeah, that q is not q the characteristic.
Okay. In arithmetic geometry seminar, so I can't throw in p and q's. Okay, so the aim is
because now we
Works.
come on, you know what?
It's clear that it's not the same.
Back to school. I think I have not used this word. Okay, so we're going to use this Hasse-Weil theorem to say, yeah, maybe I'll see it. Okay, perfect. So using this f, one can define an elliptic curve. just let x squared to be f of x. And I'll take a bit of it already. So from the definition of the chi, what we can see is each x uh, each x is zero solution, like 0 points. If say like f of x, the value is the square, non-square, and it means 2 points. It's if it's a non-zero, but it's the square, maybe just because y squared has 2 solutions, and it has exactly 1 point. F of x is exactly 0. Because like we have defined it to be 0 here. So in particular using this, what one can see is that if we count the number of rational points in the situation, what we have is the case that you're so just count x, okay, apply this chi to f, n plus 1. So this is like a magical function somehow, like as he described it. So it's like chi of f, it's either going to be 1 or minus 1. Let's just ignore the 0 case, because when it's 0, it's just 0 plus 1, which gives 1 point. Take it out. So if it's minus 1 plus 1 is going to be 0, so it's going to give nothing. If it's in this case, what we get is chi of, or if it's non-zero but squared, this is plus 1. Plus 1 plus 1 is 2. You're going to get this. So this whole information is encoded in this simple equation here, and this plus 1, because you should never forget to point it in. So what happens is you first simplify it. So all the 1 comes out over the sums of set of points of k, which is exactly 2 points. Then we have particular one can move this, shift it to the right, and use the Hasse theorem to say what value this characteristic function has. Particular from the theorem, what we know is this guy is less than or equal to q. So we can just get a bound from this. So this is one of the nice interpretation. So I'm like what this application says is that this sum which we defined, it exactly consists of like the plus and minus 1 is equally distributed somehow between these polynomials. If we just find the solutions of it, it's not like a randomly put at different points, but you can actually see there is, if you find the distribution, it's actually like a bell curve and are equally distributed. Right. So we're going to quickly see information of Weil conjectures now. So this was in 1949 when Weil made this series of conjectures on Weil data function. So what we're going to do is like we are just going to state the theorem here. We're not going to even say the sketch of proof, just going to state the theorem and give its formulation in terms of elliptic curves. That's it. So again, like fix A to be FQ. The first section is all over pen speed. So so then if we take Kn, which is the nth extension over the speed. So this particularly has of here Bn. So in particular, the number of points K and has is n-fold in this Qn of n. It is Qn. So and if you take a projective variety, so let's say take a projective variety over the space P. So in particular, P is defined as the vanishing of certain homogeneous polynomial. So while conjecture aims to say is like for such a variety, if you calculate the set of rational points of this curve. This guy is you can encode the set of all rational points of this projective variety in a nice power series function, also called the generating function. And we have to know that like while zeta function is a formulation, it's a kind of a L series function, and we believe all the L functions to obey certain nice properties, and while also prove that it is the case also here. So in particular, there are three things for L function to satisfy. The rationality, a functional equation, and Riemann hypothesis. So this is like inspired from the classical Riemann zeta function. So, first we'll define what a Y zeta function is. So here V is any smooth projective variety or the finite field FQ. Let's just put the state here. So this is just the exponential of this power series here. The set of fraction points of V over this extension V. There's like, I think there's in algebraic geometry, the usual trick. Why we define this is like we know, if we already know this, then we can somehow use this to estimate this one. So what happens is if we try to write it in terms of this, what we get is here. For example, I mean, in particular, it's not so obvious for any projective variety how to calculate this, but for here projective n space, the canonical projective n space, then this reduces to something a bit primitive. Something is then we can see that Y zeta function. Where this n is the to briefly give the statements of while conjecture. It's for the sanctity of the talk. And projective variety of dimension n. Then there are key parts in this conjecture. That's the reality is that the Y zeta function of this variety is actually a rational function. And then we have this functional equation. Says that there exists an integer So this integer is associated with the Euler characteristic of the projective writing. So such that this equation is n is the dimension. For experts who already have seen this in terms of Riemann, classical Riemann function, they can like formulate it. And then this is a Riemann hypothesis. Is that it gives a nice factorizing. Precision of this one zeta function in terms of polynomials. So you have all the you can where each is P of phi is a the coefficient. So it's a ring. With the first and last terms of polynomials. Right, and this is like the first and last orders, and for all the I in between, one can describe Pi to be the finite. So this is proposed by Well, and he proved it. And over time, people started to prove each one of this in like using different tools that were developed in mathematics. For example, Dwork in 1960, he proved this. I think like he proved the rationality using L-adic functional analysis. And Atten, Authentic, they use the L-adic cohomology to prove. They basically gave an alternative proof of what Y gave, like an equivalent proof using L-adic cohomology series. So yeah. Maybe if you want to see this Y data function for elliptic curves, I'll just write the formula down. But it's not so complicated. We have elliptic curve over the finite field. Then what we can say is like this Y data function. Yeah, so like just as on the theorem, there exists an integer. There exists a such that you can elegantly like write this Y data function in terms of this. So then now we go to the second part.
Just to before we go on, I just want to give a short remark about the Riemann hypothesis here. In the sense that okay, the important thing here is that the coefficients alpha ij have absolute value.
Yeah, you're right.
Square root.
You're right.
And this is why it is called Riemann hypothesis, because when you see this thing as you want to see this as a function over the complex numbers. So what you do is replace the variable t, usually with the variable q to the minus s.
Yeah, it's just a complex variable.
So when you work with Q to the minus x, it says that the zeros and the poles of this function are localized exactly when the real part is equal to 1/2, which is exactly like the classical case.
So now we move to the second goal, which is over number fields, which is not as big as this, probably is going to be. So the first theorem what we want to see is the Mordell-Weil theorem. So it says that if you have a abelian variety, A over here, everything is over number fields, so no finite stuff. Then you see the group, so this is called the Mordell-Weil group. For example, the set of all k rational points of our abelian variety is called the Mordell-Weil group, and it's an abelian group. So what does this theorem say is that this group is finitely generated. In particular, that's a finite basis with which you can generate all the rational points. So, like the first formulation was this Mordell theorem, which was you just replace abelian variety by elliptic curves, and instead of number field, you just take the rational number. So this was first conjecture, and then like while and some of his colleagues like generalized this for also abelian variety for number fields. Now it's proven in full generality. So yeah, so in particular, for elliptic curves, we have GPD1. So what Falting did is he exactly proved this theorem for higher genes. For circuits like this, and then he proved it for the genes. So all the things. But he proved it over Q. But I think now we also have four number features. Proof is also.
I'm not sure, but I think it's true.
But this was classically proven over Q. So it's not just finitely generated; it's actually finite. Finite group. One of the last bits. So
I can say a thing about this. It is
sure.
just again another case where you have that the elliptic curves are somehow in the middle between easy but not interesting cases like the curves of genus 0 and very interesting but too much intricate cases like genus at least 2.
It's like challenging.
Yeah.
Exactly the sweet spot. Right. So I don't wish to prove or give anything regarding the proof of that, but there's like for the next part I have to say this. So there are like two different steps one takes in proving that, and that has given over a lot of theory in mathematics. One is like first step is you prove the weaker version of that. So we prove the weak Mordell-Weil theorem. And the second thing is we use the infinite research. In particular, this uses some height functions. We're not going to see what these things are, but just for completeness, I'll say what a weak Mordell-Weil theorem is. So it just says that if every integer m greater than equal to 2, group here is I think it's finite group. Sure. I think it's a finite group. So while started proving this for m is equal to 2, and then now we also have proof for the m greater than equal to 2. So this is like the first step, and yeah, they could already see this was not enough to prove the whole theorem, and then they had to develop this differential using the fact. So in particular, using this theorem, one can actually explicitly describe what the set of Russian points are. They're exactly of two direct sums. So like sorry, two components. So one is the torsion component of the Russian points, another is the free component. In particular, this R is a game changer. So this is the rank, and till date we have not solved this. Like we don't know what given an elliptic curve or given a abelian variety, we like for sure we don't know an effective R for which this is satisfied. So I'll come back to this again. And this one now it's solved at least over Q, which is now called it was called the torsion conjecture. So, and it was solved by Mazur. So in particular, he just described what are the possible torsion subgroups this can have. So there's like he just described these are the exactly possible solutions we could have for the torsion subgroup, and that will limit the number of rational points. But still, we don't know an effective R, so this like really not satisfied. And finding this R is the BSD conjecture. Till date, there is no computationally effective evidence that this R is perfectly fine. Okay. So now we come to the Leonis curve, Sergei Leonis curve. Now I've already taken some time, so I'll just so good stands for stable, say what they mean. That stands for semi-stable. And if you already know some Mordell-Weil theory, you can already relate this because these words are actually related to the Mordell-Weil problem underlying the theory. Stable, like unstable. So, but more mathematical, like this is fine, but in literature, what we find is like good standstill, good is again, good is fine, but for what bad they use sort of multiplicative. The word is multiplicative. But for the dog, you can just remember this one. And finally, it's just additive. So I'll just give a definition, and then say a few words about it. So when do we say this is the case? So first of all, if you have an elliptic curve for number p, then one always has a reduced elliptic curve, which means like elliptic curves are defined by a y-stress function, and a reduced elliptic curves as a minimal y-stress function. So for a given elliptic curve, there will be like many models of y-stress function. So you choose the model which has a least discriminant, and that gives you a reduced kind of thing. And at least over Q, this is always possible, and it's also unique. And in particular, you can also say what the values of coefficients can take. So it's really nice. So just to keep in mind, like what is the elliptic curve behind this, that so no. Right. So we say, yeah, this picture pretty much sums up what they are. So say a reduced elliptic curve is as a good reduction if it is a smooth objective variety. It has a bad reduction if it has a node. In other words, it has mild singularities, and it's an additive. It has additive reduction if it's a cusp. So it's a severe singularity. So one can also describe this in terms of the discriminant, and this is what we'll use to end this talk. So yeah, for example, if you have So the slogan is something like you have elliptic curve defined over a field. Then you take a prime and you say when this prime is good, bad, or ugly to the given elliptic curve. So a prime is good if P doesn't divide the discriminant. So, and the C4 term is also important. It doesn't divide the discriminant. And it's bad. P still doesn't divide, but C4 divides. Again, both of them divide. Yes. So why are we studying this? This is used to define the Hasse-Weil zeta function. So Hasse-Weil zeta function is defined in like 3 cases, and those cases are exactly these ones. That's why we study this. One of the reasons why we study this also has other applications. So I'll quickly define what Hasse-Weil zeta function is, and then state what a BSD is, and then like you naturally see a connection between the zeros of Hasse-Weil zeta function at the critical step and the rank of the Mordell-Weil group which I defined. Sorry. Yeah.
And the other case, like be like P divides the discriminant, the C4 does not.
I think it's encrypted in the definitions. I haven't thought of this, to be honest. So you mean like P divides this, but C4 doesn't divide this?
Yeah, the missing one.
Okay.
Yeah, I think that bad and ugly actually have P that divides the discriminant, and then it is according to C4 dividing or not the discriminant that you either have bad
This
or
divides the discriminant.
yes.
Ah, right.
So in
Right. This doesn't. So I was trying.
So P divides when
Mhm.
when it's bad, P divides the discriminant, and then you have to. And C4 is not important for good, actually.
Wait, I'm confused. So
Good is just P does not divide the discriminant.
bad is P divides discriminant.
Yeah.
Because I've written this in terms of evaluation, so I haven't written this.
Okay, you probably inverted the.
Yeah. In terms of I've written this in terms of evaluation. So here P divides, right?
Yeah.
Okay.
And the definition of good, C4 is not important.
So, but in literature generally they call these two to be bad.
Yeah,
So
exactly.
it's good and bad, but since it's informal talk, I want to include ugly as
Yeah, because exactly as I said, you have to distinguish between semi-stable and unstable because people care about this. So you have to add the additional check of C4.
Okay.
But for good, you just have to check that P does not divide the discriminant.
Right. Thank you. So the Hasse-Weil conjecture is a sort of like we have a Weil zeta conjecture, right? It's sort of a similar conjecture, but over number fields for abelian varieties. So it was solved using the modularity problem. So, for example, introduction of modular forms gave a nice description of that, and that was also called the Taniyama-Shimura conjecture, if I'm not sure.
Yeah.
So I'll just give the definition of a Hasse-Weil zeta function. What it says is like, I'll at least give it for ellipticals or rationals. So here S is a any complex variable. So this beta is the classical Riemann zeta function. L of ES is the associated L function, which takes can be written as it can be written Euler product of primes. So to define this, you need the good, bad, and ugly. So for this piece of given prime, LP. PK. Nice. So now I'll give a definition of, no, I'll give a statement of what a BSD conjecture is, and then we'll see the connections. Maybe still, if I have time, I'll just give the quick application of that and we'll wind up. Right. So what the conjecture says it's for an elliptic curve over rational points. So the order of vanishing of this function at x is equal to 1 is exactly the rank of the group here. So yeah. So in particular, what it says is like if, so we know from the general theory that if the order is positive, order being positive means that, for example, we have a curve x minus 1 the whole square. So here, this polynomial has a positive, has an order of, as an order 2 at 1, and it doesn't have an order at any point. For example, if this one has an order, it means that by the equality, this is positive, which again, when you put it in the full equation, you have this torsion and ZR. So you know that when R is greater than 0, the group is already like, it has infinitely many modes. So that's the implication. This having an order means that the set of points are infinite. So yeah, this is very crucial. Come on. And do I still have time, like 2 minutes? So I'll just relate this to a nice application. And then now we're going to go back to school where we study about triangles. So everyone knows what this one is. It's a right angle triangle. For example, it could be a triangle. And you know, like this is where Pythagorean works. So a simple consequence is like right. So there are certain numbers called the congruent numbers. A number is called congruent if it's an area of a right angle triangle with all the sides being rational numbers. So yeah, for example, you could have, instead of this one, you could also have something like yeah. So for example, this one has an area. What way such as area? Right? Someone is really good in arithmetic, they can try to do it. So this is going to be 5. So for example, 4, 5 are congruent numbers because they are area of this area of some right angle triangle with rational lengths. So just to give an idea, these are congruent numbers. So now we are going to state the application assuming that BSD is true. Yeah, a congruent number in particular is an integer. So yeah. So it's in particular positively this area. Right. So assuming that the BSD is true, then we have the following. So there is like a testing algorithm. If you give a number, then you should be able to say when this number is a congruent number. So for example, for smaller numbers it's fine, but when it goes really big, you can't like just keep on doing it by trial and error. So BSD gives a nice formulation for finding when a number is congruent. So, and this was actually called the Tunnel's theorem. So Tunnel's theorem actually gives, like, we have three parts. Like we have the, let's say, the congruent problem on one hand. We have BSD on the other hand. We have this Tunnel's theorem on the other hand. So like assuming BSD, you know that this is true. Assuming Tunnel's theorem, you know that this is almost true. So like this one, but this actually factors into this. This is something I made up right now, but I think it should be true because this only gives a partial solution to this. And this gives a solution which, when you formulate, it's some parts of it is equal to this theorem. So somehow it has to factor through this one. So assuming this and this will give a complete theorem of congruent product. And there are like quite a lot of evidence that this should be true. So yeah. So given a positive algorithm. Remember when n is yeah. Final infinitely is the number of triples satisfying this particular equation. So this number is exactly double of the number which satisfies the equation amount. So I'm assuming BSD, then you can actually show this is actually the case. So on how they use BSD is you formulate these polynomials into an elliptic curve, and then you associate this to the number of rational points of the elliptic curve. For example, the rank. So I have something. So n is congruent if and only if that's our rational point of infinite tolerance. Only the BSD codes. Yeah, so this is like a big picture how it's all related, and to connect this whole thing, we need this set codes. We don't know if it's full. So for
Just a thing, it's LE1.
yeah. Oh, yeah. Okay. So yeah, I think it's worth looking at this conjecture because like for someone who solves this, that's like a 1 million USD waiting. So yeah, so that's okay, perfect. That's my talk. Thank you.
So if there are any questions?
I wouldn't be here. Just kidding. No, no. I just knew about BSD a few days back. So
Do we know if there are some cases, differential cases where ESD have been solved?
yeah, there are. I don't have it on top of my mind, but there are like very, for example, for rank 0, there are some nice cases where it's solved. For higher ranks, it's like for R greater than 1 is very difficult. So there are some nice characterizations when R is 0. Some people prefer, but I'm not quite sure. I actually wanted to give the current state of art, but it's so big and so time consuming because like to just say that we need to introduce a lot of machineries. So I thought I'll avoid this for this. So
Is there any other question? If not, we thank Krishna again. We resume next week. Thank you.